out two problems on condensers, then I will introduce refrigerant evaporators. So, the specific objectives of this particular lecture are to present worked out examples for thermal design of water cooled and air cooled condensers, introduce evaporators, present classification of evaporators, describe salient features of some of the important types of evaporators. And at the end of the lesson, you should be able to carry out thermal design of air cooled and water cooled condensers using suitable correlations and formula, classify refrigerant evaporators based on various criteria, describe important features of some of the important types of evaporators. So, let me begin with a worked out example. This is an example on shell and tube condenser, and the problem statement is like this. You have to find the length of tubes in a 2-pass 10-ton capacity shell and tube R22 based water cooled condenser with 52 tubes arranged in 13 columns. The heat rejection ratio is given as 1.2747. The condensing temperature is 45 degrees centigrade. Water inlet and outlet temperatures are 30 degrees centigrade and 35 degrees centigrade respectively. The tube outer and inner diameters are 14 and 16 mm respectively. So, the problem must be clear to you. It is an R22 based condenser, water cooled condenser. It has 52 tubes and 13 columns. 52 tubes are arranged in 13 columns, and the other data is as per the problem. So, now let us look at how to solve the problem. So, this is the schematic. In fact, I have last class I have shown this schematic of a 2-pass shell and tube type of a condenser, and as I have explained to you, here refrigerant is there on the shell side. Okay, you can see that refrigerant is entering at the top, and it condenses as it comes in contact with the tubes, and the liquid refrigerant goes out from the bottom, and water enters from the bottom like this. Coolant is nothing but the water, and it flows through these tubes. Since it is a 2-pass, the same water again will flow through the condenser tubes. Okay, so it comes here and again it goes back to the condenser tube. That is why you call it as a 2-pass condenser. That means the water makes 2 passes as it flows through the condenser. And in the problem it is mentioned that there are 52 tubes, okay, and they are arranged in 13 columns. Now, the first thing we have to do is we have to find out the properties of R22 and water, because we have to evaluate the heat transfer coefficients and all. So, these are the properties at average temperature. For water, viscosity is given as 7.73 into 10 to the power of minus 4 kg per meter second. Thermal conductivity is given as 0.617 watt per meter Kelvin, and density is 995 kg per meter cube. Specific heat of water is given as 4.19 kilojoule per kg K, and Prandtl number is given as 5.25. PR is Prandtl number. And for R22, the average properties are viscosity is 1.8 into 10 to the power of minus 4 kg per meter second. Thermal conductivity Kf is 0.0779 watt per meter Kelvin. Density is 1118.9 kg per meter cube, and latent heat of vaporization is 160.9 kilojoule per kg. This is at the condensing temperature, and it is also given in the problem that the fouling resistance on water side and thermal conductivity of copper are fouling resistance is 0.000176 meter square Kelvin per watt, and the thermal conductivity of water is given as 390 watt per meter Kelvin. So, this is how the problem is stated. So, now we have to find out the required length of each tube. Okay. So, first the step is to find out what is the required heat transfer rate in condenser. You know that required heat transfer rate in condenser is nothing but QC is equal to product of heat rejection ratio HRR into refrigeration capacity, and the heat rejection rate ratio is given as 1.2747, and the refrigeration capacity is given as 10 tons. So, we convert that into kilowatts. So, this is 10 into 3.5167 kilowatt. So, from this equation you find that the condenser heat transfer rate is 44.83 kilowatt. Then let us find the required mass flow rate of water. So, from energy balance we can also write QC is equal to MW CPW into TWO minus TWI, whereas you know MW is the mass flow rate of water, CPW is the specific heat of water, TWO and TWI are exit and inlet temperatures of water. And we know here we know the values of QC, we also know the value of Cp, we also know the temperatures. So, if you substitute those values, you find that the total mass flow rate of water is 2.14 kg per second. Now, this 2.14 kg per second is distributed in many tubes. Okay, since it is a 2-pass condenser with 52 tubes, water flow through each tube is given by this formula. This is m subscript Wi is the water flow through each tube, that is equal to mw by 26. Why do we get 26? There are 52 tubes, but it is a 2-pass condenser. That means in one pass the water flows through 26 tubes. So the total flow rate is given by 2.14 kg per second. So through individual tube the flow rate is 2.14 divided by 26. So that is 0.0823 kg per second. Now once we know the water flow rate and once we know the water properties, we can calculate the Reynolds number for water side. So as you know, Reynolds number for water side is rho Vd by mu. This can also be written in terms of the mass flow rates. So in terms of mass flow rate, it is 4 into mwi divided by pi di mu w, where mwi, as you have seen, is the mass flow rate through each tube, and di is the internal diameter of the tube, and mu w is the viscosity of water. So if you substitute these values, because everything is known to you, if you substitute these values, you find that the Reynolds number for water side is 46882.6. Since this is greater than 2300, we can this is turbulent flow. So we have to use the turbulent flow correlations for finding the heat transfer. So let us find the heat transfer coefficient on water side. In fact, in last class I have mentioned that if it is turbulent flow, we can use Dittus-Boelter equation or Cedertate equation. So in this problem, let us use Dittus-Boelter equation. Dittus-Boelter equation, as you know, is nothing but Nusselt number is equal to 0.023, Reynolds number to the power of 0.8, Prandtl number to the power of 0.4. So we know Reynolds number, we also know the Prandtl number. So if you substitute these values, you find that the Reynolds Nusselt number for water side is 68.96. So once you know the Nusselt number, you can find out the heat transfer coefficient, because heat transfer coefficient is nothing but Nusselt number into thermal conductivity of water divided by the diameter. So if you substitute these values, you find that heat transfer coefficient on water side is 3039 watt per meter square Kelvin. Now let us find the heat transfer coefficient on the condensation side. So condensation heat transfer coefficient. Since condensation is this is a shell and tube type of condenser, so obviously water is flowing through the tube, so condensation is taking place outside the tubes, and this is since nothing is mentioned, let us take this as a horizontal shell and tube type of condenser. So let us use the correlation for horizontal condensation on horizontal tubes. So in fact in the last class I have mentioned that we can use the classical correlation given by Nusselt. In fact Nusselt's correlation is valid for laminar flow. So here this is valid. In fact you can cross check that you will find that it is valid here. So let us apply the Nusselt's correlation for finding the condensation heat transfer coefficient. So what is Nusselt's correlation? So this is the Nusselt's correlation for laminar film condensation outside horizontal tube. I have explained this in the last lecture. Okay, here as you know, this is the thermal conductivity of saturated refrigerant. This is the density of saturated refrigerant at condenser temperature, and this is acceleration due to gravity. This is the latent heat of vaporization at that temperature and pressure. N is the total number of tubes in a row, and D naught is the outer diameter of the tube on which condensation is taking place. Mu f is the viscosity of the saturated liquid, and delta T is nothing but the temperature difference between the refrigerant and the wall, okay, surface, let us say. Okay, so this is the Nusselt's correlation, and here H naught is in watt per meter square Kelvin, and all other units are in SI. So you have to use the SI units. This you have to be careful while using the units. So we know from the problem we know everything except delta T. So let us find H naught. Okay, so if you substitute number of tubes per row, we have to find out, that is capital N. Since it is mentioned that there are total number of there are 52 tubes and they are distributed in 13 rows. So number of tubes per row is nothing but 52 by 13, that is 4. So if you substitute this 4 and the other property values, you will find that the Nusselt correlation, from the Nusselt's correlation, H naught is given as 2175 divided by delta T to the power of 0.25. Okay. So here delta T, as I have already mentioned, is nothing but the temperature difference between the condensing refrigerant and the surface. This is not known to us. So what we have to do is we have to use a trial and error method. Okay. Trial and error method means initially we use a guess value of delta T, find out H naught, find out U naught and all, and finally you have to cross check whether the guess value is correct value or not. I will show you that procedure now. Before that, for water cooled condensers without fins, the overall heat transfer coefficient is given by this formula. This also I have explained in the last class. As you know, this is the convective resistance of the inside, this is the fouling resistance on water side, and this is the resistance offered by the wall, and this is the external resistance. Okay. Now everything is known to us because A naught and AI and all can be expressed in terms of diameters. So diameters are given to us, properties are also given, and this fouling resistance is also mentioned in the problem statement. So we know everything. Okay. So if you substitute everything, you find that the overall heat transfer coefficient is like this: 1 by U naught is equal to 0.0005781 plus 1 by H naught. H naught is not fully known to us because we do not know what is the delta T. Okay. So as I said, we have to go for a trial and error method. So first let us take a initial guess value of 5 degree centigrade. So once you take a guess value of 5 degree centigrade, condensation heat transfer coefficient H naught is equal to 2175 divided by delta T to the power of 0.25. So delta T is 5 degrees. So from this we find that heat transfer coefficient is 1454.5 watt per meter square Kelvin on the refrigerant side. Once you know this, you can substitute this in the expression for overall heat transfer coefficient, and you find that 1 by U naught is equal to 0.0012656 meter square Kelvin per watt. That means the overall heat transfer coefficient U naught is equal to 790.2 watt per meter square Kelvin. So we have found the U naught, and we know that for the condenser we can write this equation: QC is equal to U naught A naught into LMTD, which is equal to 44.83 kilowatt. QC is 44.83 kilowatt. Now, so we have to in order to find out A naught, we have to find LMTD because U naught is known to us. So LMTD, as you know, is for a condensation process. LMTD can be written like this: TWO minus TWI divided by natural log of TC minus TWI divided by TC minus TWO, where, as you know, TC is the temperature of the refrigerant, TWI and TWO are the inlet and outlet temperatures of water. Okay, so all these things are known to us. So if you substitute these values, you find that the LMTD is 12.33 Kelvin. Okay, so if you substitute the values of LMTD and U naught in the expression for QC, then you find that the area required area, that is outer area, is 4.6 meter square. Now, as I have already mentioned, you should not stop this thing here, because this value we got by taking an initial guess value of 5 degree Kelvin for delta T. Okay, so now we have to see whether delta T is really 5 degree Kelvin or not. If it is not 5 Kelvin, we have to go for the next trial. Okay, so let us calculate what is the delta T. Now, delta T can also be written in this manner: delta T is equal to QC divided by H naught into A naught, because you can write QC in terms of QC can be written in terms of outer convective heat transfer coefficient, outer area, into refrigerant temperature minus surface temperature. Okay, this is nothing but delta T, right? So H naught is nothing but condensation heat transfer coefficient, which is known to us. A naught just we have computed. Okay, so if you substitute everything, you can find out what is the calculated value of delta T. That's what we are doing now. Okay, so if you substitute the values for QC, H naught and A naught, you find that delta T calculated is 6.7 Kelvin. So you find that the guess value is, we have started the solution by taking an initial guess value of 5 degree Kelvin, but when at the end, when you calculate delta T, you find that it is 6.7 Kelvin. Since there is a difference of 2 degrees between the guess value and the calculated value, we have to go for a next trial. Okay, so in the next trial, what we do is, let us assume a delta T of 7 Kelvin. Okay, and repeat the calculations. So what we do is, as I said, since the calculated value is not equal to the assumed value, we have to repeat the calculation with delta T is equal to 7 Kelvin. So this is the second trial. So once you assume delta T as 7 Kelvin, again you have to find out H naught, because H naught is expressed in terms of delta T. So once you find the H naught, you find the overall heat transfer coefficient. Once you find the overall heat transfer coefficient, you find out area, and from the area again you find out what is delta T calculated, and you compare delta T calculated with again the guess value. Okay, so this process has to be repeated till you get the converged values, right. So from the, if you repeat the calculation with 7 Kelvin guess value, you find that the delta T calculated will be 6.96 Kelvin now. Okay. So this is almost equal to 7 Kelvin. So you can stop here, but if you want more accuracy, of course you can again repeat the calculation by taking a third trial value, right. But since this difference is very less, we need not go for third trial. Okay. So since this value, as I said, sufficiently close to second guess value of 7 K, we may stop here. Okay. So for 7 K temperature difference, we obtain the value of U naught to be 754 watt per meter square Kelvin. So once you know the value of U naught and LMTD and QC, we find the value of A naught equal to 4.82 meter square. Okay. Ultimately, we have to find the length of the tube. Okay. So A naught is nothing but there are 56 tubes. Okay. So total area is 56 into pi d O into L, okay, where pi do is the outer diameter of the tube, right. There are 56 tubes, so we use 56. L is the length of this thing which is unknown to us, but d naught is the outer diameter which is known to us, 16 mm. Okay. So if you substitute those values, you find that the required length is 1.713 meter. Okay. So this is a how you have to do the design of a shell and tube condenser. Of course, this is not a complete design, this is only a thermal design of shell and tube condensers. Okay. So you have to proceed in a systematic manner, first by getting the required properties, right, and then using the correct formula, and then calculate the various quantities, and then you have to go, as I said, you have to go for trial and error method. Okay. And when you are using a trial and error method, you have to take use intelligent guess values. Okay. You should not use unrealistic guess values, then it may take a long time. You have to do the calculations for many trials, you have to take many trials. Okay. So use the value judiciously, then it will converge within 2-3 steps, right. Now let me explain the design of an air cooled condenser. Again, let me read the problem. You have to determine the required face area of an R12 condenser for 5-ton refrigeration plant. The condensing temperature is 40 degrees centigrade, the system COP is 4.9, and refrigeration effect is 110.8 kilojoule per kg. Air at an inlet temperature of 27 degrees centigrade flows through the condenser with a phase velocity of 2.5 meter per second. The inside and outside diameters of the tubes are 11.26 and 12.68 millimeter respectively. Fin efficiency is given as 0.73, and the other dimensions, these are the spacings and thickness of fins. Okay. Spacing between two tubes in a row B is given by 43 mm, and C is 38 mm, D is 3.175 mm, and the thickness of the fin is 0.254 mm. Okay. So what is given here? Capacity is given, and condensing temperature is given, COP is given, and refrigeration effect is given. Okay. And then air inlet temperature is given, outlet temperature is not given, and phase velocity of air is given as 2.5 meter per second, and inner and outer diameters of the tubes are given, and other heat exchanger dimensions are given. Okay. So as you know, this we have discussed in the last class. I have shown you typical, I said this is the typical fin and tube type of condenser, and as I said, this is the face area. Okay. This is the face area. We have to find out what is the face area, right, and we have also defined certain parameters. For example, as I was telling you just now, B is nothing but the center to center distance between two consecutive tubes in a row, right. This value is given. C is, this is the side view. Okay. C is the center to center distance between two rows, right. So that is C, and D is the center to center distance between two consecutive fins, and T, as I said, is the thickness of the fin, right. So all these parameters are given to us. So we have to ultimately find out the face area, and we also know the phase velocity. Okay. Phase velocity is mentioned as 2.5 meter per second. Now first thing we do here is, let us find out various heat transfer areas. All these areas have been defined in the last lecture, so you can refer to the last lecture for these formulae. Okay. So I am just giving the formula here. First is the bare tube area AB, AB is given by D minus T by BD into pi D naught, and D is nothing but fin to fin spacing, so that is 3.175 millimeter minus 0.254 is the thickness of the fin, and B is the spacing, center to center spacing between two tubes in a row, that is given as 43 mm. And so if you substitute these values, D naught is the outer diameter of the tube. So if you substitute all these values, you get this value for AB, and remember that this is defined as meter square per row per meter square face area. This is very important, okay, the unit. So everything, all the areas we are expressing as meter square per row per meter square face area, okay. Then let us calculate the fin area AF. Fin area AF, this is the formula. Again everything is known to us, D is known, C is known, D naught is known, B is known. So if you substitute everything, you get the fin area to be 22.087 meter square per row per meter square face area, okay. Now let us find out what is the minimum flow area. Minimum flow area is, as I said, is nothing but the area between the two tubes, okay, where the velocity becomes maximum and the flow area becomes minimum, okay. So that is defined as this, D minus T by D into 1 minus D naught by B, and again everything is known. So if you substitute that, you find that minimum flow area is 0.6487 meter square per row per meter square face area. Then total area A naught is nothing but AB plus AF, that is bare tube area plus fin tube area. So that is found to be 22.94 meter square per row per meter square face area, okay. And the internal area is AI, and the formula AI is, for AI is pi di by B, and this works out to be 0.82266 meter square per row per meter square face area, okay. Then we have to find out the hydraulic diameter, because we want to find out the Nusselt number and Reynolds numbers. Hydraulic diameter is defined, if you remember, as the 4 into minimum flow area divided by the wetted perimeter, okay, and the formula for that is given like this. Okay, so this is the formula for minimum flow area, hydraulic diameter dH, and C is known to us, AC is the minimum flow area, and A naught is the A naught is also known, where this is the total area, okay, that is 22.94. So if you substitute everything here, okay, this should be 22.94. I have rounded off it, okay, it is actually 22.9393, but I rounded it off to 22.94. So you find that the hydraulic diameter is given as 4.2984 into 10 to the power of minus 3 meters, and we also need these area ratios for calculating the overall heat transfer coefficient, okay. So this area ratio A naught by AI is the total area divided by the internal area, that works out to be 27.8843, and AB by AF, that is the bare tube area divided by fin area, is 0.3715. So now we have found all the required areas. Now let us find out the condenser heat rejection rate. So in the last problem for water cooled condenser, the heat rejection ratio is given directly, okay, but in this problem it is not given directly, but the COP value is specified, and we know that heat rejection ratio is nothing but 1 plus 1 by COP, okay. So we have to find the heat rejection ratio first, and from the heat rejection ratio we can find out the heat transfer rate at the condenser, okay. So that is what I have done here. The condenser heat rejection rate QC is equal to HRR into QE, where QE is the refrigeration capacity, that is 5 tons, and HRR is 1 plus 1 by COP, and COP is given as 4.9, and QE we know 5 ton, convert that into kilowatts by multiplying into 3.5167. So if you multiply that and substitute the values, you find that the required heat rejection rate at condenser, that is QC, is equal to 21.17 kilowatts. Now we have to find out what is the mass flow rate of refrigerant. To find out the mass flow rate of refrigerant, we know the refrigeration capacity, and also the refrigeration effect is specified, okay. So we know that if you do an energy balance for the evaporator, neglecting the kinetic and potential energy changes, we know that the refrigeration capacity is nothing but mass flow rate of refrigerant into refrigeration effect, okay. So refrigeration effect is specified. So substitute the value of refrigeration effect and the refrigeration capacity, you find that the mass flow rate of refrigerant is equal to 0.15869 kg per second, okay. So from now first let us find out the condensation heat transfer coefficient. For that we need the properties of R12. So the properties of R12 I have not mentioned here, but the properties have to be evaluated at condensing temperature, and condensing temperature is specified as 40 degrees centigrade. So you have to find out the saturated properties of R12 liquid and vapor at 40 degree centigrade. Okay, so I have used those values, and using those values I have found these non-dimensional numbers. Okay, first I have found the Prandtl number of refrigerant, that is Cp mu by K, and this is the Prandtl number for the saturated liquid. Okay, F stands for liquid. Okay, so you have to use all the liquid values, right? So if you use these values, you find that Prandtl number for the liquid refrigerant is 3.264, and the Reynolds number for the gas, okay, G is for the vapor or the gas, okay, that is again can be written in terms of the mass flow rates, 4 into m dot divided by pi di mu z, and this Reynolds number is calculated when all the mass is in vapor form. Okay, so you have to use the total mass flow rate here, right? So this Reynolds number is the Reynolds number when all the refrigerant is in vapor form. Similarly, Reynolds number of the fluid is calculated assuming that all the refrigerant is in liquid form. Okay, that is REF. So if you substitute the values, you find that this is the Reynolds number of the refrigerant vapor. Similarly, Reynolds number of the refrigerant liquid is this. Okay, so we got the Reynolds numbers and Prandtl number. Then to find the condensation heat transfer coefficient inside tubes, we use Dean, Akers and Crosser's correlation, which assumes complete condensation. In fact, this is a new correlation. In the last lecture, I have shown two other correlations, Chato and Chadok's correlation and other correlation. Okay, but here I am using a different correlation. Okay, this is because I want to present as many correlations as possible, right? So let us calculate the condensation heat transfer coefficient using this Dean, Akers correlation. And this correlation is valid for under the assumption that the condensation is complete. Okay, so this correlation defines a modified Reynolds number REM, and this modified Reynolds number is defined like this. Okay, this correlation, if you notice, correlates Nusselt number in terms of Reynolds number and Prandtl number. So this is the basic correlation, Dean, Akers and Crosser's correlation. So you can see that this looks like a Dietz-Boelter equation. Okay, you have a constant here, Re to the power of 0.8 and Pr to the power of 1 by 3. Okay, only difference is the Reynolds number that I am using here is a modified Reynolds number. Okay, it's neither Reynolds number of the vapor nor the Reynolds number of gas. It's a modified Reynolds number, and modified Reynolds number formula is like this. It is written in terms of the Reynolds number of the refrigerant liquid and the density of the saturated liquid and density of the saturated vapor, rho f and rho z. So densities can be written in terms of specific volumes, and we know the specific volumes from the property data, that is at 40 degree centigrade, and REF also we have found. So you can find out what is the modified Reynolds number, and Prandtl number is also known to us. So if we substitute all these values, we can find out what is the Nusselt number. So substituting various property values and Reynolds number, we find that Reynolds number, modified Reynolds number is 431,383, and Nusselt number is 1265.9, and condensation heat transfer coefficient HI is 8206.7 watt per meter square Kelvin. Okay, so that's how we have found the condensation heat transfer coefficient. Now let us find the air side heat transfer coefficient, because for calculating the overall heat transfer coefficient you require heat transfer coefficient on the refrigerant side, heat transfer coefficient on the air side. Okay, so let us find out the heat transfer coefficient on the air side. Remember that this is a finned plate fin type of a condenser, so you have to use suitable correlations for plate fin type of heat exchanger. Okay, in fact, if you remember last time I was mentioning that Case and London have given several correlations for different types of condensers. So we will be using the general correlation suggested by Case and London. Okay. In fact, if you remember, the Case and London correlation is the Reynolds number is defined in terms of the maximum velocity, and maximum velocity takes place where the flow area is minimum. Okay, so maximum velocity is nothing but the face area. You can show that it is nothing but the face area divided by face velocity divided by minimum flow area. This comes from your continuity equation. Okay, how did you get this? Let us say that you have two tubes here. Okay, and this is the minimum flow area AC. Okay, and at this point the velocity is u max, right? And let us say this is the at the face. At the face you have the face area. Okay, or area between two tubes, and you also know the velocity, face velocity. Okay, and from mass balance we know that AU is constant. Okay, so U max is, you will find that phase velocity divided by AC, because we are writing AC in terms of per meter square phase area. Okay, so that is why the phase area term does not come here, because we are doing all the calculation per meter square phase area. Okay. So you find that using that we find that the maximum velocity is 3.854 meter per second. So the phase velocity is 2.5 meter per second, but by the time the air comes between the two tubes, its area of cross section gets reduced, so its velocity increases to 3.85. Okay. Then we find the Reynolds number. Reynolds number is U max into hydraulic diameter divided by nu. So whatever we have calculated, the hydraulic diameter and all will be used now. Okay. So we know the hydraulic diameter value, we have computed this. This is the kinematic viscosity, and U max is the maximum velocity, that is 3.854 meter per second. So we substitute that, you find that Reynolds number is 983.6. Then we, as I said, we use the general correlation suggested by Case and London, which is given as Nusselt number is H naught dH by K, that is equal to 0.117, Reynolds number to the power of 0.65, Prandtl number to the power of 1 by 3. So we know Reynolds number, we know Prandtl number, so we can substitute this. So we find that the Nusselt number is 7.835, and heat transfer coefficient H naught is equal to 51.77 watt per meter square Kelvin. Now overall heat transfer coefficient for plate fin type heat exchanger, the formula is like this. This formula was mentioned in the last class also. So here you have the fouling resistance on the refrigerant side, you do not have any fouling resistance on the air side, that means outside fouling resistance is not there. Okay. And you know various this thing A naught by I, and these are the area ratios. Ri and R naught are the inner and outer radii of the tubes, and eta f is the fin efficiency which is known to us, H naught is the external heat transfer coefficient, Hi is the internal heat transfer coefficient. Okay. So if all these things are known to us, we have already computed all these things. So if you substitute those values, you find that overall heat transfer coefficient is 31.229 watt per meter square Kelvin. Okay. And now we have to find out the LMTD, because we have to find out the area. So for that we have to find the LMTD. Okay. Again we have to do some trial and error method here, because we do not know what is the outlet temperature of air. Neither we know the outlet temperature of air, nor we know the mass flow rate of air. Okay. Since we do not know these two parameters, we cannot calculate the LMTD directly. So what we have to do is we have to assume either mass flow rate or the outlet temperature. So it is easier to okay, it is all the same, but let us assume the outlet temperature of air. Okay. The outlet temperature of the air you have to assume in such a way that it should not be greater than the condensing temperature, obviously, because heat transfer has to take place from refrigerant to air. Okay. So in this problem, let us assume a value of 35 degrees for the outlet temperature of air. So once you assume the outlet temperature of the air, inlet temperature is given as 27 degrees, condensing temperature is given as 40. So we can calculate what is the LMTD. So LMTD is 8.3725 degrees centigrade. Okay. So once you know the LMTD, we can find out what is the total external area. Okay. A total. How do we know this? Because QC is nothing but U naught into total external area multiplied by LMTD. So LMTD is computed 8.3725, and QC is 21.17, and U naught is 31.229. Okay, I am multiplying here because this 21.17 is kilowatts. So I am converting everything into watts, because U naught is in watt per meter square Kelvin. So if you do that, you find that the total external area is 80.976 meter square. Okay. So this is the total area, and remember that this can have many rows, right. So total area means total area of the condenser, that means area of all the rows, right. And so far nothing has been mentioned about the rows, right. And in the last class I have mentioned that the number of rows can vary anywhere between 2 to 8. Since this is not a very large capacity system, it is a 5-ton capacity system, let us take the number of rows to be 4. Okay. So I am assuming the number of rows to be 4. Once you assume the number of rows to be 4, total area is nothing but A face area into number of rows into A naught. why are we writing like this? Because A naught is nothing but the total area per meter square face area per number of rows. Okay, so that's why you get this kind of formula, and A naught is known to us. Number of rows are assumed to be 4, and A face area is not known to us, but A total is just now we have calculated 80.976. So if you substitute all these values, you find that face area is 0.882 meter square. But this may not be the correct face area. You have to check, because you have assumed that the outlet temperature to be 35 degrees centigrade. Okay, whether that is right or wrong, you have to check now. How do we check that? We calculate the mass flow rate of air. Mass flow rate of the air is nothing but, if you apply the continuity equation, it is nothing but rho into A phase into V, where V is the phase velocity, that is 2.5 meter per second, and A phase is computed to be 0.8824 meter square, and rho is the density of air, which is 1.1774 kg per meter cube. This is the mean density, right? So if you substitute these values, you find that this is the mass flow rate of air, right? Once you know the mass flow rate of air, you can easily calculate what is the outlet temperature. How can you calculate that? We know that for the condenser you can also write QC as mass flow rate of air into Cp into delta T. So delta T is nothing but QC divided by mass flow rate of air into Cp. Cp I have taken here as 1.005. Okay, so and the mass flow rate of air we have computed, and this is a QC, right? Here you need not multiply into 1000, because this is in kilojoule per kg Kelvin. So you find that delta T we have obtained it to be 8.11 degree centigrade, right? Now what is the delta T is 8.11 degree centigrade, means what is the outlet temperature? Outlet temperature is nothing but T outlet for A of air is T inlet of air plus delta T. Okay, T inlet is given as 27 plus 8.11, this is 35.11 degree centigrade. So you find that coincidentally the whatever you have calculated is very close to whatever you have guessed. Okay, so the guess value and calculated values are coming very close. Okay, so if this accuracy is sufficient, you can stop the trial and error procedure at this point, and you can take this face area as the required face area. But if you want very high precision, then you can go for a second trial by taking the outlet temperature to be, let us say, 35.1. Okay, so you can continue this. But sometimes if you get accuracies of this kind of accuracy, there is no point in really going for more and more number of trials, because remember that there is always an element of uncertainty in the calculation of heat transfer coefficients. Okay, they themselves may give uncertainties could be as high as about plus or minus 25%. Okay, so there is no point in really looking for very close accuracies in areas, right? So that is what I have mentioned here. So T air out as calculated is 35.11 degree centigrade. Since the guess value is close to the calculated value, we may stop here. For better accuracy, calculations have to be repeated with second guess value of 34.1 degree centigrade. Okay, and there is one thing you must keep in mind: the values obtained will be slightly different if other correlations are used for HI. As I said, a large number of correlations are available for estimating the heat transfer coefficients. For example, on the condenser side or on the air side. Had you used some other heat transfer correlations, you might have got slightly different results. Okay, that's what I mean by saying there is a lot of uncertainty, right? If you want, you can check by using other correlations and see what value you are getting. Okay, so this is the procedure for estimating for design thermal design of condensers. Okay, if you proceed in a systematic manner, the problem is very simple. Okay, so at this point I stop my lecture on condensers, and let us go to the next important component, that is evaporators. So I will give a brief introduction and classification of evaporators in this lecture. Okay. So as you know, evaporator like condenser is also a heat exchanger. In an evaporator, the refrigerant boils or evaporates, and in doing so absorbs heat from the substance being refrigerated. The name evaporator refers to the evaporation process occurring in the heat exchanger. Now let us look at the classification of evaporators. In fact, you can classify evaporators in many ways. There are several ways of classifying the evaporators depending upon the heat transfer process, or depending upon the refrigerant flow type, or depending upon the condition of heat transfer surface, etc. Okay. For example, you can classify them as either forced convection type or natural convection type. And as you know, in what is a forced convection type evaporator? In forced convection type evaporator, just like forced convection type condenser, A fan or pump is used to circulate the external fluid. External fluid could be water or air or any other media. Okay. So, you need a pump or fan for circulating this external fluid. Okay. And make it flow over the heat transfer surface, which is cooled by evaporation of refrigerant. This is the forced convection type evaporator. Natural convection type, as you know, in natural convection type we do not use either a fan or pump, and the flow circulation takes place because of buoyancy effects. The buoyancy effects are induced due to density differences, which are caused by temperature difference. Okay. This is nothing but the natural convection type evaporator, just like natural convection type condenser. Okay. In natural convection type evaporator, refrigerant always boils inside tubes, and evaporator is located at the top. You have to locate the evaporator at the top because you are relying on the natural convection. Natural convection means what happens is, when you are keeping at the top, a warm air comes in contact with the evaporator, it becomes cold. Once it becomes cold, its density increases. Once its density increases, because of the buoyancy effect, it tries to settle down. When it settles down, the warm air from the bottom rises up, and warm air goes to the evaporator, it gets cold, and again it comes down. So, this cycle is repeated. Okay. So, to continue maintain this cycle, you have to keep the evaporator at a height. The temperature of fluid which is cooled by it decreases. I am just explaining what is the mechanism. The temperature of fluid which is cooled by it decreases and its density decreases. As a result, the fluid moves downwards due to buoyancy, and the warm fluid rises up to replace it. Okay. You can also classify the evaporators based on the refrigerant flow, whether it is taking place inside the tubes or outside tubes. The heat transfer, this is very important because the heat transfer phenomena, okay, just like condensation is entirely different if evaporation or boiling is taking place inside the tubes or if it is taking outside the tubes. Okay. The phenomena is different, the correlations will be different, and the values of heat transfer coefficients also will be different. So, it is very important to keep this in mind and use the suitable correlations. Okay. So, this is another way of classifying. The third way of classifying is by classifying them either as flooded type of evaporators or dry expansion type of evaporators. In flooded type evaporators, liquid refrigerant covers the entire heat transfer surface. Okay. So, this is known as a flooded type evaporator, and the refrigerant leaves evaporator as liquid vapor mixer. Okay. And what is the dry expansion type? In a dry expansion type, the refrigerant leaves the evaporator in vapor form, and not the entire heat transfer surface area is covered with liquid. Okay. There are some area is covered with the vapor. Okay. So, this is known as dry type. Now, let me explain the salient features of some of the important types of evaporators. So, let me begin with natural convection type of evaporator. Okay. Natural convection type of evaporators are mainly used in domestic refrigerators and cold storages. Since flow is buoyancy driven, evaporator has to be kept at the top. You might have for example, everybody must have seen it in old type refrigerators, not frost free type. In conventional type refrigerators, the evaporator is kept at the top. Okay. In fact, this is nothing but evaporator comes freezer box. Okay, evaporator, and it also acts as a freezer compartment or freezer box. Okay. So, evaporator tubes are kept here. It can be a roll bond type or tube and plate type, and you store the food products everywhere. Frozen food is kept here, and other foodstuffs are kept here, vegetables, fruits, etc. Okay. So, the gravitation is in this direction, this is the top. So, since you are keeping the evaporator at the top, the air close to the evaporator becomes cold, and since its density increases, the air will come down. Okay. So, if you see from the side, the evaporator will be something like this. Okay. So, cold air comes down, right, and as it comes down, it comes in contact with the food products kept at the bottom, and it takes the heat from the food products and it becomes warm. Once it becomes warm, again it rises up. Okay. Once it rises up, again it comes in contact with the evaporator surface, it becomes cold, and again it comes down. So, this natural circulation is maintained by keeping the evaporator at the top. Okay. Normally, these are unfinned when used in cold storages. As I said, these are mainly used in domestic refrigerators and cold storages. In domestic refrigerators, fins are added, but in cold storages, fins are not used. Okay. a sufficient space should be provided all around the evaporators for airflow. This is very important, just like your condensers, flat back condensers or wire and tube type of condensers, you are relying on buoyancy effects for airflow. Okay, so the delta T's are not normally very high, so the potential for the airflow is generally small. So if there is large resistance, then the airflow gets affected adversely. Okay, so if you want to have good airflow, you have to provide sufficient space all around the evaporator so that air can flow with minimum resistance. Okay, so that's why you might have seen in the domestic refrigerator that they don't put the evaporator right at the top. That means there will be some space all around the evaporator so that air can flow all around the evaporator. Okay, and baffles are provided to separate the warm air and cold air plumes. Now, what are the advantages of natural circulation evaporators? Evaporator occupies less floor space. This is very important, especially in cold storages and all, because floor space, if the system occupies a lot of floor space, then valuable floor space is lost, because you could have stored some products in that floor space, and by storing more products you could have earned more money. Okay, so floor space is very valuable. So when you are using a natural convection type of evaporators in cold storages, they are kept at the right near the ceiling. Okay, so it does not occupy any floor space, right. So this is one of the advantages of natural circulation type evaporators. Second advantage is they can operate for longer periods without defrosting, and they are simple to make and easy to maintain, because especially in cold storages and all, they are plain tubes. Okay, normally they are unfinned, so they will be simply welded at the site. So there are no fins, nothing, just you have to take the pipes and weld the pipes at the site. Okay, and the maintenance is also easy and very useful when low air velocities and minimum dehumidification of the product is required. Since you are relying on natural convection and the delta T available for natural convection, obviously you won't find any air blast or anything. Okay, so the air velocity will be very small. Once the air velocity is small, there is no danger of products getting dried up too much. Okay, this is one typical problem with forced convection type of evaporators, because air velocity is high. High air velocity means high heat and mass transfer rate, so drying of products take place, whereas in natural convection type this problem is not there. Okay. However, there are certain disadvantages. The disadvantage obviously is that you require very long lengths, because the overall heat transfer coefficient is typically small. This is small because you are relying on natural convection. Hence, higher refrigerant inventory and higher pressure drops. Once the required tube length becomes large, you have to put large amount of refrigerant inside the system. Okay, once you put large amount of refrigerant inside system, there are other problems. The cost will be more. Okay, and if the refrigerant is toxic and flammable, it will have safety problems. Okay. In addition to that, there are other problems like pressure equalization takes a long time, and defrosting also takes long time. Okay, so these are some of the disadvantages of having long lengths. Okay. In addition to this, if you have long refrigerant tubing, pressure drop also will be large. So if you want to minimize the pressure drop, you may have to go for parallel circuits. Okay. Now let me quickly explain the second type, that is the flooded type evaporators. They are typically used in large ammonia systems. The refrigerant enters a surge tank through a float type expansion valve. The compressor directly draws the flash vapor, which improves the performance. As you know that once your flash vapor is not allowed to go to the evaporator, performance improves. We have seen this in multi-stage systems. And the liquid refrigerant enters the evaporator from the bottom of the surge tank. The mixture of liquid and vapor flows along the evaporator tubes. The vapor is separated as it enters the surge drum or surge tank. Okay, unevaporated liquid is recirculated. So let me quickly explain this. So this is the flooded type of evaporator. Okay, so this is the evaporator portion, right? Let us for the timing, let's assume that this is used for, let us say, cooling air. Let us say, so you have a fan and fins and all, air is blowing over this. So we have the component surge tank here, and refrigerant from the condenser enters the surge tank through the float valve. This float valve acts as an expansion device here. Okay, this is expansion device used here. And what is the purpose of this float type of valve? It always maintains the required level of refrigerant in the surge tank. Okay, if when the level falls, the valve will open more refrigerant will come here. So normally this is connected to a condenser or receiver condenser. Okay. And you can see that when the refrigerant enters at this point, it is vapor plus liquid. because due to flashing across the expansion device some vapor would have been generated. So, you have both vapor and liquid, but what you are doing is by separating vapor and liquid in the surge tank, you are allowing only liquid to go to the evaporator, and vapor instead of going to the evaporator it directly goes to the compressor. Okay. So, that is how you can improve the efficiency of the evaporator. So, as you can see from the picture that only liquid refrigerant goes through the evaporator, and as it flows through the evaporator it takes heat from the surroundings and vapor is generated. Okay. So, you can see the vapor bubbles. So, you find that at the outlet of the evaporator again you have vapor liquid mixer. This is the feature of a flooded type of evaporator. Not all that refrigerant that goes to the evaporator will evaporate. Okay, there will be a large amount which is unevaporated. The unevaporated amount will simply recirculate. So, whatever vapor is there, again that vapor plus whatever vapor is generated here, both will be compressed by the compressor. Okay, so this is the flooded type evaporator. You can see that there is a lot of liquid in the evaporator, and the evaporator surfaces are always wet. That will give you higher heat transfer coefficient on the refrigeration side. So, this is the advantage of flooded type of evaporator. Okay. And mass flow rate through evaporator is not same as the mass flow rate through compressor, and the ratio of these two mass flow rates is called as recirculation factor F. And if you apply the mass balance for steady state, whatever mass is leaving the surge tank must enter the surge tank. Okay. Then that means what you have to do, you have to apply a mass balance across the surge tank. Okay. From that you can easily show that the recirculation factor F is 1 minus x4 divided by x. What are x4 and x? X4 is the quality of refrigerant at the inlet to the surge tank, and X is the quality of the refrigerant at the outlet of the evaporator. Okay. So, this is by applying the mass balance across the surge tank. Okay. So, once you know the qualities, you can calculate what is the circulation factor. Circulation factor will be greater than 1. That means more refrigerant circulates through the evaporator than is evaporated. Okay. Now, since liquid, what are the advantages? Since liquid refrigerant is in contact with whole of evaporator surface, the refrigerant side heat transfer coefficient will be very high. Sometimes a liquid refrigerant pump may also be used to further increase the heat transfer coefficient. The lubricating oil tends to accumulate in the flooded evaporator, hence an effective oil separator must be used immediately after the compressor. Okay. Right, I will stop the lecture here and I will continue this lecture in the next class. Okay, in the next class I will give you formula for calculating the heat transfer coefficients and area of evaporators. Okay, thank you.